Hello dear friends, welcome to the lecture of differential calculus. We are studying partial differentiation. In this lecture we shall study Euler's theorem on homogeneous functions, and before that we shall see what is the definition of homogeneous function and some examples, and I have written this definition and example here. Also I have written Euler's theorem statement to save the time, and this is simple. The meaning and definition of homogeneous function is simple. A function f of xy is said to be homogeneous of degree n if it is expressible, or it can be written as x power n f of y upon x. So that means function of y upon x, or in other way, if it can be written as f of tx comma ty is equal to t power n f of x comma y. T is any variable, and this is the meaning or definition of homogeneous function. Now here are the examples. This is the first. F of x comma y function is 2x cube plus 4x square y minus 5xy square, and by observation we can say what is this function's type. It is homogeneous function of degree 3. And meaning is each term, when it is written in a polynomial form or this algebraic form, each term must be of the same degree, and that is the meaning of homogeneous. It must have the same property, same degree here, and this term is of third degree. This x square y term, the degree of x term is 2, degree of y term is 1, and this is in product, means there will be addition of the degree, and this is the third degree term, and similarly this is also third degree term. But this is by observation, but according to the definition we can write the function like this: f of x y is equal to, here we should take the maximum power of x common, and here what is the maximum power of x is this cubic power, and the term is x cube. We have taken x cube common, and what remains in bracket, you see 2. This is a simple algebraic simplification, you can understand it. X cube is taken throughout common, means we have to divide by x cube for each term, and the first term becomes 2, plus the next is x square y divided by x cube is y upon x, and next is 5, xy square divided by x cube becomes y square divided by x square, that I have written y upon x whole square, and thus this is in this form: x power n a function of y upon x. Each term is written function of y upon x, means each term must be in the form of y upon x. This is y upon x, and this is square of y upon x or constant, and thus this is a function of y upon x, and what is outside term is x cube, and therefore this n is the degree, and thus the 3 is the degree of this term. So we can easily check by the second definition also. See, if I consider this function, then what will be f of tx comma ty for this function? Wherever x and y are there, write tx and ty. So that will be 2 tx cube plus 4 tx whole square ty, y is to be written as ty, minus 5 tx ty square. And now see, here which term of t is common, can be taken as common. Now we can observe here it is t cube, here also t square into t, that is t cube, and here also t into t square, that is t cube. So t cube can be taken common, and if you take t cube common, what remains in bracket? That is 2x cube plus 4x square into y. T cube is taken common, and 4x square into y, and that is minus 5, and t cube taken common, what remains is xy square, and exactly this is same as this one, that is f of xy, and thus t power n, this n is the degree, here n x power n. If this can be written in two ways, either this way or this way, and that in the first expression the power of n, power of x is the degree, here power of t is the degree, and that is t cube, the third power term. And so that means homogeneity can be checked by the first definition or the second definition. So now we will see this next example. See, the second example is f of x comma y is x plus y divided by root x plus root y. Here also it can be checked like this. So see, the numerator is homogeneous of first degree and the denominator is homogeneous of half degree, and if there is quotient then there will be a subtraction of the indices, 1 minus half, and that is half. So this is a homogeneous function of half degree, or according to this definition it can be written as, take the term of x common from numerator, that is maximum power term of x, that is x only, and if you take x common then in bracket 1 plus y over x remains. Similarly, from the denominator take root x means x to the power half common, and in bracket what remains is 1 plus under root y divided by x. So you can verify this, and what is the power of x is 1 and the power of x at the denominator is half. So 1 minus half, that is half, and here also we have checked the numerator power is 1, denominator numerator degree is 1, the denominator degree is half, and if there is quotient then there will be subtraction of these degrees, and that will be degree of the whole expression, that is half. So this is homogeneous function of degree half. So by observation we can decide the degree and so on. So see, if I consider this function, say x square plus y square divided by x plus y. So what about this function? This is also homogeneous, and what will be the degree of this function? Numerator is homogeneous function of second degree and the denominator is homogeneous function of first degree, and the degree of the whole expression will be again 2 minus 1, that is 1. So in this way we can decide the degree by either by observation or by using the definition in this form or the second form. So this is about homogeneous function, and now we shall see what is the theorem, Euler's theorem on homogeneous function. Euler is a famous mathematician and this theorem is named after him. If z is equal to capital F of xy, actually capital F of xy, and here also you should see a function capital F of xy can be written in this form, or this is a function of y upon x, it will be different function of y upon x, and here we have written z is capital F of xy is a homogeneous function of x comma y of degree n. This is a homogeneous function, that means it satisfies this definition. Then the result is x into partial derivative of z with respect to x plus y into partial derivative of z with respect to y is equal to nz, where this is true for all xy in the domain of the function. So function takes values from certain set, that set is called domain, and xy are in the domain of the function. Now we prove the result. It is necessary that z must be function of degree n. So z can be written as, z is homogeneous function of degree n. Z can be written as, by definition, z is a function, homogeneous function of degree n, so therefore we can write z as x power n f of y upon x, function of y upon x. And now after writing z in this form, we shall prove this result. To prove this result, we require the partial derivative of z with respect to x and also the partial derivative of z with respect to y. We suppose this as 1, and first we differentiate this partially with respect to x. So differentiating partially with respect to x. So what we shall get is partial derivative of z with respect to x is equal to, and here we shall have to use the product rule, because this is product of two terms, functions x power n, and second function is f of y upon x. Use the product rule, and the product rule can be used like this: the derivative of the first, second as it is, plus first as it is, derivative of second, or any way you can use it, and that is the derivative of the first is n x power n minus 1, and this function f of y upon x as it is, plus, and now what will be the second term? First as it is, that is x power n as it is, into derivative of this function. So but this function is written in the form of f notation, and derivative of f we denote by f dash or f prime, and that is f prime y upon x into derivative of inner function y upon x with respect to x. Y is constant when we are differentiating partially with respect to x, and therefore we have to write the derivative of 1 by x. What is derivative of 1 by x is negative 1 over x square, and y is constant, therefore this will be negative y over x square or divided by x square. So this much is the partial derivative of z with respect to x. We have used the product rule, also the chain rule. The chain rule of derivative is important, and here to write the derivative of f of y upon x, it is f dash of y upon x, outer function's derivative multiplied by inner function's derivative, that is negative y divided by x square. So this can be simplified, and but you see we will simplify, and also we will do this step also. We multiply it by x. We have obtained this, we want this term. So multiply this by x. Multiplying by x, we'll get x dou z by dou x is equal to, and if you multiply by x, this power increases by 1, that means this becomes x power n, that is n x power n f of y upon x, and see there is minus sign, this is in product, minus, and this is x to the power n divided by x power 2, means x to the power n minus 2, and we have multiplied by x, means the power again increases by 1, means final power of x will be x power n minus 1 into y, and f dash of y upon x. So this is the term x dou z by dou x. We write this as second. Now, so we you might have understood the next procedure or next step will be form this term, and to form this term first we should have to get the partial derivative of z with respect to y. Again now differentiate one partially with respect to y. So I shall now write here differentiating z partially with respect to y, that is from 1. Differentiating 1 partially we get, see I shall write here partial derivative of z with respect to y, and that is equal to, now you observe when we differentiate z partially with respect to y, x is to be treated as constant. So that means x power n remains constant. There is no need to use the product rule now. This is a constant term and that remains as it is. Only we need to differentiate y, f of y upon x with respect to y. And what is derivative of f? We have written f dash y upon x into the derivative of inner function with respect to y. And when we differentiate y upon x with respect to y, x is constant, means 1 upon x remains constant, and into derivative of y, that is 1. So this is only 1 by x, and thus this much is the partial derivative of z with respect to y. Now we obtained this term, we want to multiply it by y. So multiplying by y, we get, now see, y dou z by dou y is equal to, and we can see this is x power n divided by x, means the power will be x to the power n minus 1. One power will be reduced, and we have multiplied by y, means y into x power n minus 1, f dash of y upon x, and we suppose this as third relation. Now what to get the theorem's result, see, observe second and third. So what we have to do from second and third, second is here and this is third. So now to get the theorem statement, this one, so we shall add 2 and 3, and if we add 2 and 3, what we shall get? Adding 2 and 3, we get left side addition, I shall write here x dou z by dou x plus this is left side of 3 y dou z by dou y is equal to, on the right side, see the addition, what will be the addition on the right side? This is n x to the power n f of y upon x minus x power n minus 1 y f dash of y upon x plus x power n minus 1 y f dash of y upon x. In addition, these two terms gets cancelled. They are of opposite sign. Here it is plus and here it is minus. So the sum is 0 and only this remains. That is n into x power n f of y upon x. And you see, what is x to the power n f of y upon x? This is x to the power n f of y upon x, that is exactly z, and this is equal to n into z. This follows by 1, using 1 here, and this is what we wanted to prove. X dou z by dou x plus y dou z by dou y is equal to nz. See, and this proves the theorem. Thus we have proved the Euler's theorem. And it is easy to prove, but the theorem is important, and we should remember the statement of the theorem, that is, if z is function of homogeneous function of degree n, then x, there are two terms on the left side, x dou z by dou x plus y dou z by dou y is equal to nz. Now we shall state a corollary of Euler's theorem. I shall state the corollary here. Corollary means a result that is that can be deduced or that can be obtained from the main result or theorem. Corollary, if again the statement will be the same, if z is a homogeneous function, function of xy, x comma y of degree n, then x square dou to z by dou x square plus 2x into y dou to z by dou x dou y plus y square dou to z by dou y square is equal to n into n minus 1 into z. So this is the corollary of this is a corollary of Euler's theorem. Now what is the difference in the main theorem and this result? Actually it is a corollary, means we have to obtain the result from the main result theorem. How to obtain this result from this one? So we shall first state the result again. By Euler's theorem we have this first result, and proof of this by Euler's theorem. write the theorem as same because z is homogeneous function. So theorem follows, and x dou z by dou x plus y dou z by dou y is equal to nz. This is the Euler theorem. And now from this result, to get this result, we can see, observe the derivatives in this result. This is the second order derivative. This is also the second order derivative of z. It is mixed with respect to x and y. And this is second order derivative of z with respect to y. So therefore we shall differentiate this partially with respect to, first with respect to x, and then secondly with respect to y. So I shall suppose this as 1 and differentiate partially with respect to x. We get and here we have to use the product rule because it is product of x and dou z by dou x, and thus I can write first function as it is. Product rule we shall use. First function I shall write as it is, derivative of the second, that becomes partial derivative of dou z by dou x means dou by dou x of dou z by dou x, and that is dou square z by dou x square. This we have seen the second order derivatives, and therefore this becomes dou square z by dou x square, partial derivative of this, plus, but we have to use product rule here. This is first term in the product rule. Now derivative of the first, that is 1, and second as it is dou z by dou x. So we must use the rules of differentiation correctly. So this much is the derivative of the first term plus, and secondly here we are differentiating partially with respect to x, therefore y is constant and there is no need to use the product rule. We write y as constant as it is, and we have to write only the derivative of this with respect to x, and that derivative will be again dou by dou x of dou z by dou y, and see derivative of this with respect to x, that is dou square z by dou x dou y, and I shall write here dou square z by dou x dou y. So this much is the derivative of the second term, and on the right side it is n is constant and partial derivative of z with respect to x is dou z by dou x. So this we have written x into dou square z, etc. Now I shall write this as second. Differentiate now 1 partially with respect to y, because this term also we need dou square z by dou y square. For that we differentiate 1 partially with respect to y, and see what is the result that we shall get. Differentiating 1 partially with respect to y, we get, see the first term. Here when we differentiate partially with respect to y, x is constant and x remains as it is. So but dou z by dou x will not be constant. You remember that it may contain y, and therefore this is a function of z that may also contain y, x and y. So therefore we don't know whether it is entirely of x or y. It may be of both x and y, and therefore its partial derivative is to be written in this form, dou by dou y of dou z by dou x. So that is the partial derivative of this with respect to y, and x is constant, x will remain as it is, and this derivative is dou square z by dou y dou x plus. So this much is the derivative of the first term. Now for the second we have to use the product rule. Here when we have differentiated partially with respect to x, we have used product rule for this because both are functions of x, and here now this is y, function of y, and this is also function of y, so use the product rule. So that is y as it is, derivative of this is second order derivative of z with respect to y, that is partial derivative, and plus derivative of y is 1, and second this as it is dou z by dou y. So this much is the derivative of the left side partially with respect to y, and right side is n partial derivative of z with respect to y. So this we have obtained as the third result. Now you see how to get the required result from these expressions. This expression contains the second order derivative of z with respect to x, and the coefficient here is x, but here we want x square. And also you may observe this term is a second order derivative of z with respect to y, and the coefficient is y square. So here it is y. That means we have to multiply second by x and third by y, and then we will add the terms. So multiplying 2 by x, 3 by y, and adding we get. Now see, it will be easy to write, so I shall multiply and write the term as x square dou square z by dou x square, and plus x dou z by dou x. I shall write the second equation's left side first after multiplying by x dou z by dou x, plus this will be xy dou to z by dou x dou y. So this much is the product of left side by x. Now plus I shall write the product of the left side of 3 with y, plus y into x. This is y into x dou to z by dou y dou x, plus y into y square dou to z by dou y square, and plus this is y dou z by dou y. So this much is the addition on the left side of 2 and 3, plus or now right side. Right side is, see, this is nx dou z by dou x, and plus ny dou z by dou x. So shall I take n common, y dou z by dou y. And now we will simplify this and use the first relation also. So what is the simplification of this? That is, see, x square dou to z by dou x square plus this term I have written, and these two terms are equal. X into y and y into x is the same. Similarly, we have written a remark earlier, dou to z by dou x dou y is same as dou to z by dou y dou x in general, and therefore these two are equal and their addition will be double term, that is 2x into y dou to z by dou x dou y, plus, so these terms are written. Now I shall write this term, y square plus y square dou to z by dou y square, and this much I shall write on the left side. And what are the remaining terms? You see, remaining terms are these two, x dou z by dou x, y dou z by dou y. I shall shift that term on the right side, and that term will be, or sum of these two terms is plus x dou z by dou x plus y dou z by dou y is, this is written on the left side itself, and right side is n times x dou z by dou x plus y dou z by dou y. Now we see the value of this term from 1 is simply nz. So this is nz and this is nz, and I shall transfer this term on the right side, and therefore the expression becomes, see, the expression on the left side, so we will get this result now, that is, see, x square dou to z by dou x square plus 2xy etc plus y square into this, and this is n into nz minus nz. So that is equal to n into nz minus nz, and this is by 1. This is by 1. 1 is here. X dou z by dou x plus y dou z by dou y is equal to nz. And what is the right side? Right side can be simplified. And that is, take here nz common, or that can be written as n into n minus 1 into z. See, this is n square z minus nz, and this is the required result. Hence the result. So thus we have proved the Euler's theorem and also the corollary on Euler's theorem.